In this video, we're going to start looking at sets, set theory, and set operations, introduce a bunch of terms and vocabulary, and then talk about some basic operations we can do on these things called sets. So again, we're going to learn the basic vocabulary and notation of set theory, learn and apply the union, intersection, and complement operations, and then we're going to use Venn diagrams to diagram and represent some things we're doing in set theory. So first, let's start with a bunch of definitions. A set is a collection of objects or things, and those things are known as elements. So any collection of objects or things, those things could be numbers, they could be words, they could be letters, they could be anything at all. A set is well defined if there is a way of determining whether a particular item is an element of the set or not. So for example, here are two examples of sets: the set of all math classes at URI and the set of all fun math classes at URI. The first one is a well-defined set because it is clear whether something belongs in that set or not. Math 107 belongs in that set. Bio 101 does not. It's not a math class. The set of all fun math classes at URI is subjective, so it's not very well defined. So this would be not well defined. You could change this to be well defined. You could say the set of all fun math classes at URI according to Ben. That might be something that's well defined, but that one's not. And note that when we're working with sets in this class, we're going to be dealing with well-defined sets almost exclusively. So we're going to list elements in a set separated by commas in these curly brackets. And we're going to say that X is an element of a set S. We usually represent sets with capital letters. We say X is an element of a set by doing X in S. And that in symbol is like a weird looking E. We say the cardinal number of a set, we denote that with N of A, is the number of elements in that set, or we could just think about the size of the set. And I think it's worth talking about why do we have a special name for this called the cardinal number. Well, when we're talking about finite sets, which is what we're going to be doing at the beginning of this section, when we're talking about finite sets, there's no difference between the size of the set and the cardinal number. It's just the number of elements in that set. It's a pretty straightforward thing to think about. However, when we start talking about infinite sets, which we're going to be looking at later on, this idea of how big a set is not a easy topic. And then we have this special term that talks about the differences between different infinite sets. So just looking forward to why do we have this weird terminology for the size of a set? And there is a reason. We say that two sets are equal if they contain exactly the same elements. And with that, I think it's worth talking about another thing about sets, which is, let's look at this set of numbers. So this set, 1, 2, 2, 2, 3, that is the exact same thing as the set 1, 2, and 3. And the point I'm trying to make here is that repetition, spell that correctly, repetition does not matter. It doesn't matter how many of one thing we have in a set, we're only going to write it once. So 1, 2, 2, 2, 3 is really the exact same thing as just 1, 2, 3. We're going to often look at sets and represent sets with this set builder notation. So let's look at two examples. The set of all positive real numbers, we could represent in this set builder notation as, in curly brackets, X, this symbol right here, this little vertical bar, is read as such that. So it is all X such that X is positive, that's X greater than 0, and X is a real number. X is in the real numbers. And that is a little symbol for the real numbers. Sometimes writing it down just kind of like that with double lines on the side. So again, When we read this set builder notation, it is the set of all x such that x is greater than 0 and x is a real number. Let's look at the next set. Next set is A, E, I, O, U. And we could say that's going to be all letters such that the letter is a vowel. And actually, this is a good example of a set that may not be well defined, because we know that sometimes Y is a vowel, so it's not clear whether Y should be included in this set or not. We're going to deal with kind of sets with letters, and we're going to specifically indicate whether Y is a vowel or not, or whether it's in both vowels and consonants, or is it something else. So actually, this is a good example of a not well-defined set. So some more definitions. The empty set, denoted a circle with a line through it, is the set with no elements. And it's important to note that the cardinal number of that set is 0. There are 0 elements in the set, so its size is 0. Again, that's saying that the size of the empty set is 0. That's what that notation means. Opposed to the empty set is the universal set. That's denoted a capital U, and that's the set that includes everything. What does everything mean? Well, everything changes depending on the context of the problem. So for instance, in our first example in the set builder notation, U is all numbers. Whereas in the second one, U is all letters. And what U is, the universal set, could change completely depending on problem to problem. And sometimes it's defined, and sometimes it's just implied in what it is in a certain context. But it's worth noting that the empty set and universal set are diametrically opposed. One has no elements, the other has all of the elements. And these are going to be very important sets that we look at a bunch in set theory. We'll talk about a couple of examples where both of those are really necessary when we talk about certain operations. Next, we say that A is a subset of B. We denote that A, we call this subset of B. It's like a less than or equal to sign, kind of. If every element of A is also an element of B. So let's look at an example. We have the set A, B, C is a subset of the set A, B, C, D, E. So because everything in the left is also in the right, then that is a subset. So it's a piece of a bigger set. It's a small chunk of the bigger set. So let's look at an example talking about some of the definitions we've had, and then we'll go into more operations. Consider the following sets of U.S. states. And note that when we talk about this, the U.S. states, that's going to be our U. This is all U.S. states is the universal set. Now let's just think about some of these sets, and we'll talk about ways to sort of look at subsets of each of them. So the first set is the states Rhode Island, Massachusetts, Vermont, New Hampshire, Maine, Connecticut. Sometimes this is known as the New England states. And note that sometimes New York is included in that list and sometimes it is not. I guess I'm not including it here. I'm not trying to make any claim or not taking any position on anything. B is the state such that the state is not in the contiguous U.S. Again, this is set builder notation. We're saying all states such that the state is not in the contiguous U.S. That is the lower 48 states. That's the continental U.S. So that is just the states Alaska and Hawaii. The next set is the states such that the state begins with the letter C. So there are 3 states in there. There is California, Colorado, and Connecticut. D, the states such that the state has the word island in the name. Well, there is only one state such we have that, and that is Rhode Island itself. And finally, states such that the state begins with the letter R. Again, there is only one state with that property, and that is Rhode Island. So let's talk about some subsets and some ways we can kind of link these together. So note that D is equal to E. These 2 sets are equal. They contain the exact same elements. Even though they're defined in different ways, they're the same set. We have a bunch of different subsets. We can say that D is a subset of A. Therefore, we can say that E is a subset of A. Rhode Island is also a New England state. Note that we cannot say C is not an element or a subset of A. And we commonly write not a subset with a subset sign with a line through it. That's a common notation for not something. So the reason that's true is because even though Connecticut is in both states, so let's look at this a little bit further. So even though Connecticut is in both sets, Colorado and California are not in A. So therefore, it's not a subset. Only one thing agrees. All of these, all are subsets of U. A, B, C, D, E, U, and the empty set are all subsets of U. That's always going to be the case. And note that the empty set is a subset of everything. We'll say of all of these. And that's always the case for the empty set and the universal set. All right, let's move on. We're going to be able to use Venn diagrams to talk about some properties and some operations we've done on set theory, on sets. So note that we did this with logical expressions, and in fact, in the last page of this video, we're going to look at the relationship between these logical expressions we have and these operations in set theory and talk about how we're really doing just about the same thing in a different context. But let's talk about just set theory right now. Let's talk about a subset. So A is a subset of B. If we think about that as a Venn diagram, we have this big circle B that represents the set B. It's inside of the big set U, which is the rectangle. And note that we have a set A, which is inside of B. It is a subset of B. So if you have any element in A, it is also an element of B because it's in the circle B as well. There are 2 different kinds of subsets we have. We say that A is a proper subset if there is an element of B that is not an element of A. This means that A is not equal to B. But we say that A is an improper subset of B if A is equal to B. And we denote those with a subset sign with a line underneath or not. And note that it's really the same idea as less than or equal to. So for instance, we say that 2 is less than 4. We also say that 2 is less than or equal to 4. But note that 4 is not less than 4, but 4 is less than or equal to 4. And there's something special about it being equal that may be important. So as long as they're not equal to proper subset, we can use either the line underneath or not, just as we could say 2 is less than or equal to 4. But an improper subset means that you could have equality as well. So now to our big three operations: intersections, unions, and complements. So the intersection of two sets A and B, and there's our keyword there, and, is going to be A, this little upside down U symbol, B, is equal to the set of all x such that x is an element of A and x is an element of B. If we think about the Venn diagram, we have a circle for A, we have a circle for B, and if it's in both A and B, then it has to be the intersection of those two circles, and this little area we have shaded in the picture. So this is the intersection of two sets. The keyword there is and. The union of two sets A and B is A union B, U, like a U symbol. Note that union is going to give us a U without a tail, not U with a tail. U with the tail is something different. That represents the universal set, so just be careful of that. So the union is x, all x, such that x is in A, and the keyword here is or x is in B. That means we're going to shade everything in the circle with A, and we're going to shade everything in the circle with B, and we're going to put them together. So A union B is kind of both, or. So we say that two sets A and B are mutually exclusive, and sometimes we're going to say they're disjoint, if the intersection between them is equal to the empty set. And this is maybe a good example of where the empty set can really come in handy. We're talking about the intersection between two sets, and how do you represent that intersection is nothing? We use a set. That set is the empty set. Note that there are slight differences between the definitions of mutually exclusive and disjoint, but at this point, they're really the same thing to us, so we're not going to worry about those differences. So in a Venn diagram, this means that we have two circles that don't overlap at all. There's nothing in common between them. The intersection is the empty set. To understand this relationship between the intersection and union, let's do an example. Consider the following sets: A, which is 1, 2, 3, B, which is 2, 4, 6. So first, let's find the intersection, A intersect B. We look at everything that's in common between both sets. 1, 2, 3, and 2, 4, 6. The common element is 2. When we do the union, it's like we're just taking both sets and we are mashing them together. However, since we don't want to repeat things, then if it's in both sets, we're just going to write it once. This is going to be 1, 2, 3, 4, 6. So let's think about the size of these sets. The size of the intersection is 1, just one element in there. And the size of the union is 5. There are 5 elements in there. And when we think about these two sets, we're going to see on the next page that there's a formula that we can use to relate those together. And we'll come back to this page to view this example after we introduce that formula. So here it is. Thinking about the cardinal numbers of intersections and unions. The size of the union, A union B, is equal to this everything in A plus everything in B minus the size of the intersection. And what we're doing is when we add everything in A and then we take everything in B and we add those together, that means that we are double counting the intersection. So we need to subtract it off once, so you only count each part once. So let's look at the previous example to see where that comes in. When we found the union, A union B, if we just kind of put those two sets together, it's like we have the set A here, and then the set B. And we could think about that. We just have the size of A plus the size of B is 6, but we can see that we double counted the 2. So to get rid of that, we have to subtract off that intersection just once. So here, the size of the union was equal to the size of A plus the size of B minus the size of the intersection. That is 3 things in A, 3 things in B, minus 1, the thing in common that we count twice, and that gave us our 5. Let's do a harder example with that formula. In a class of 80 students, 42 have taken a Math 107 course, 26 have taken a Bio 101 course, 14 have taken both. How many people have taken neither course? So before we even get to the question, let's just talk about some notation we're going to have here. We're going to call the set of people who have taken a Math 107 course, we'll call that set T. We'll call the set of people who have taken a Bio 101 course, we'll call that set B. The people who have taken both is going to be the intersection between T and B. And when we think about how many people have taken neither course, what we're really looking for is not the union, but we're going to use the union to find it. So let's draw a little picture of our Venn diagram. 2 overlapping circles, T, B, and the universal set. When we think about the union, so that is T union B. If we want to find how many people have taken neither course, that is everything that is outside of those circles. And since we know that there are 80 people total, then how many people have taken neither course is going to be 80 students minus the size of T union B. If we know all the people that have taken either course, take those away from the total number of people, we have the people that have taken neither course. So how do we find the union? Well, we use our formula. The size of the union is equal to the size of the two sets together minus the size of the intersection. So the size of T is 42, the size of B is 26, the size of the intersection is 14. So total we have 42 plus 26 is 68, minus 14 is 74. 54. We're subtracting. 68 minus 14 is 54. So therefore, how many people have taken neither course is going to be 80 minus 54 is 26 people. We're going to do a bunch of problems like that in the next video, looking at this relationship and talk about some more complex problems where we have 3 sets together instead of just 2. So now we're going to talk about complements. And actually, before we get to this page, just think about something that we did in this last problem. And that is that we looked at, to answer this question, we looked at how many people were not doing something. So to answer the question about how many people have taken neither course, we actually answered the question of how many people took either course and then subtracted it from the universal set. And that is exactly the idea of a complement. So note that this is a complement with an E in the middle, not an I. Saying you look very nice today is a compliment with an I. This is a complement. If you complement something, you work with that, you help each other out. So the complement of a set A, denoted A to the C power, or the A with a bar on top of it, is the set of all elements in U, but that are not in A. And in set builder notation, this is going to be A complement is the set of all X such that X is an element of the universal set and X is not an element of A. Also note that another way to denote the complement could be A prime, A with a little apostrophe on it. We won't use that at all. In fact, we're just going to use the little C notation all the time. So the size of the complement, this is really the key part here, is the size of a complement is going to be the size of the universal set minus the size of the set itself. And that's what we did on the previous page. We looked at 80 minus the size of the union. All right, so with the complement in mind, let's think about this example. Find the following sets and the size of those sets. So the first one is the set of all letters before X in alphabetical order. So that's going to be A, B, C, D, all the way to X. And although we could represent that set like that, we could also just think about that this is going to be the complement of all the letters after X, or including X. So X, Y, Z are all the letters that are not before X, and we could just take the complement of that set. That's a way to represent that set. So the size of this set is going to be all letters, 26, minus 3. There are 23 letters in that set. And we only had to write it using just 3 letters. The complement of A union B, if A is the set of vowels and B is the set of consonants. And here we're including Y in both. So Y is both a vowel and a consonant here. So let's think about, what does A union B represent before we think about its complement? Well, if you take all the vowels and all the consonants and you put them together, that's just going to give you all of the letters, the entire universal set. So the complement of that, U complement, is going to be the empty set. And the size of the empty set we said was 0. The opposite of everything is nothing. U complement is the empty set. And finally, let's think about the complement of A intersect B. Well, here, what letters do we have that are both vowels and consonants? That's going to be just the element Y. And we're thinking about Y complement is a set that we're looking for. We could write that all the letters but Y. And the size of that is going to be 26 minus the 1 letter in there, 25 letters total. So 3 examples where using the complement was helpful in determining our answer. So looking at Venn diagrams and how we can use Venn diagrams to help us think about more complicated sets where we're bringing more than one operation together, let's look at the following two examples. A intersect B complement and A union B complement. So what we're going to do is we're going to shade both parts here. We're going to shade A and we're going to shade B complement. Now we're going to put those together with either the union or the intersection. So shading A is just going to be shading everything in the circle A. B complement is everything that is not in the circle B. First, let's do both of these for A. B complement is everything that is not in the circle B. So we're going to shade everything else. Including the stuff in A. Do that over here as well. And then for each of these, we are looking at either the union or the intersection. So for the first one, we have the intersection. So we're going to look at where the shading is together, where we have shaded both. And that's going to be this little crescent moon shape right here. This is A intersect B complement. It's where we have shaded both A and B complement. The union is where we've shaded either one of them. So it's going to be everything but this crescent moon shape. So here is a union B complement, everything but that little part of B. So we could say that this is that little crescent moon complement. All right, and finally, let's talk about the relationship between set theory and logic. Logic is what we talked about in the first unit of this course. We talked about things like disjunction, conjunction, negation, and a conditional. We have these symbols for them. We talked about its relationship between the words or, and, not, and if, then. And what we just introduced with set theory is going to be the exact same thing. Union is the idea of two things together with the word or. And it's really the same idea with a disjunction in a different context. We're not talking about simple statements and putting them together, but sets and putting them together. Intersection is related to the word and in a conjunction. Complement, we already said the word not a whole bunch, so it's just like that negation. And a subset is like a conditional. If we say if something's in A, then it's also in B. If, then. So again, the only difference here is the context of what we're talking about. In logic, we're talking about simple statements and combining simple statements. In set theory, we're talking about sets and combining different sets. And we could even see the notation here, especially for the union and intersection, is very similar, and that's not by coincidence, that's by design. So lastly, let's think about the following logical biconditionals. These are if and only if statements where both sides are equal. And it's going to be relating our set theory and our logic. We have X is in A union B is the same thing as saying X is in A or X is in B. For the intersection, we say X is in the intersection if X is in A and X is in B. We say X is in A complement is the same thing as saying the opposite, the negation of X is in A. So not X in A. We could even say that's the same thing as saying X is not in A. Same idea. And then finally, the conditional and the subset. A is a subset of B is the same thing as saying if X is in A, then X is also in B. If X is in the smaller set, it has to be in the bigger set. So in this chapter, we're going to start using all these operations and these vocabulary terms to look into sets a little more deeply, similar to what we did with logic in some ways.